now on segment 6 of module 1, and the title of this segment is how to understand the world, play with it. And this actually makes a lot of sense. If you look at a small child, how does it understand the world around it? It plays little games, and then it builds an understanding of the world, how the world works, and that's how the child develops. And what we are going to see is somewhat similar to that. In this, but in a much more simplified sense. Let's say we want to try and understand and build a model, a probabilistic model of some system. And but we don't know what the right model is. So what we do is we play with it. We repeat some experiment to try to understand what the model should be, and over the course of time we get a good sense of what the model should be, and that's the goal. And we want to look at this in this segment is Bayes' law, which provides the basis for this sort of playing with the world in order to get the best, to build the right model. Okay, and this finds a lot of application, especially in Bayesian statistics. And so let's, without further ado, let's look at a simple example where this sort of context plays out. So here's what we mean by the world around us. We have 3 coins. One of them is biased. It is biased so that it will land heads with probability 2/3. The other 2 are unbiased. But the problem is we don't know which one is biased and which one is unbiased. So we're just going to assume that they're all randomly permuted. And so this is the world that we are given. But we would like to build an improved understanding of this world, build the right model. We want to find the biased coin. We want to know what the biased coin is. And so what would be a natural thing to do? Well, let's try to play with the world. Try to play with these coins. Toss them around to see which one is likely to be the biased coin. So this is what we mean by playing with our context. Okay. So let's so we can do that, but and we can get a sense of which one is biased. But we want to have a rigorous quantification of our understanding, and that's where our attempt at modeling the situation comes in. Okay, so what we do is before we start experimenting with these coins, we start with some basic understanding, a reasonable understanding of which coin is biased and which one is not biased. And so this is before we start any experimentation, so it's often called the prior. Okay. And let's say we toss each of these coins once and ask ourselves, what is the outcome? Well, say the outcome is heads, tails, and tails. Okay, the 3 coins. Now, having seen this outcome, okay, we would like to make some inference about which coin is biased and which coin is unbiased. It will not be a deterministic inference, but it will be a probabilistic inference. And this, because this is an inference that we make after the experiment has been conducted, it's called the posterior understanding, or the posterior model. Okay, so before the experiment we had a prior model, and after the experiment we get a posterior model, and then we but this is only based on one experiment, so maybe we could try to improve upon this posterior understanding. And how do we do that? We just simply repeat the experiment a few times. So here's a pictorial representation of how we can do that. We start with a reasonable prior model. We conduct an experiment, and based on the outcome of the experiment, we develop a posterior model. But now this posterior model is an improvement over the initial prior model. So this posterior, we therefore convert that into our prior, so and conduct the experiment again. And when we conduct the experiment again, we get an even more improved posterior model. And with that as our prior, we repeat the experiment, and so on and so forth. And at some point, we're going to reach a stable situation where there is not much more improvement, and so that kind of indicates that we've reached a good posterior model, and we break out of this loop. So this is very typical Bayesian inference in this context. So so the question is, can we rigorously quantify our confidence in our understanding? So we have done these experiments a few times. What is how good is our understanding? These are some of the questions that we would like to answer. And the key underlying principle that will help us approach this question is Bayes' law. And so to understand Bayes' law, let's consider some events E1 through En. The probabilities of these events is what we are interested in. Okay, this is the model that we want to build. And we are going to assume that these are disjoint events. And B is some other event. This is usually the outcome of some experiment. Okay. And based on this outcome, we want to update the probabilities of these events. Okay. So we basically want to get these probabilities of these events EJs. Okay. And this, given that after the experiment we got this B as our outcome. So this is what we want. Okay, and this is a conditional probability, so we can apply the formula. That's very straightforward. And Bayes' law is very simple. You just look at the denominator. That's just the probability of the event B. And now you expand that out using the law of total probability. And similarly, the numerator, you apply the formula for conditional probability. But important thing is, in the right hand side, you're going to condition on the EJ values, on the probabilities on the EJ events. So what you notice here is, on the left hand side, we want the probability of the events EJ conditioned on the outcome of the experiment. But on the right hand side, what we are going to do is switch the conditionalities. So conditioning on the EJs, we want to plug in the probabilities of get the probabilities of the event B. And why is this important and useful? Well, because the EJs on the right hand side correspond to our prior model. So based on our prior assumption, we can actually compute things of this nature. Given that we have a prior understanding of EJ, we will be able to compute the probability of B. So this is something we will typically be able to handle, and that's the type of probabilities we have on the right hand side. And because on the in the right hand side we have probabilities, conditional probabilities of this type, we can actually compute them. And when we can compute them, what Bayes' law gives us is a way to compute the left hand side, where the conditionality is reversed, and the focus now is on getting the probabilities of the EJs, which is the posterior model. Okay, let's actually work out an example, and things will become a lot more clear. Okay, so let's go back to the coin tossing example. We have 3 coins. We don't know which one is biased. One of them is. So let let EI denote the event that the ith coin is biased. Okay, so E1 means the first coin is biased, E2 means the second coin is biased, and E3 means the third coin is biased. And of course, these are all disjoint events. And we want to understand and build a model of which coin is the biased coin. Okay. Initially, we don't know anything about these coins. So the reasonable prior to begin with is that with probability 1/3, each one of them is the biased coin. Okay, that's pretty much all we can do because we don't know any more information about the coins. Okay, so this is our prior model. Now let's try to apply Bayes' law. For that, we will need to run some experiment, and we need to be able to use the outcome of that experiment, that event B, in order to make some improvements to our model. So basically, compute the posterior model. So now let's say we toss each coin, and B is the outcome of each of those three coins. Now based on B, we would like to understand what is the probability of EI given that B came out as the outcome. Okay, so this is what we want to compute. Okay, these are the posterior probabilities, and let's look at an example to see how this can be worked out. So let us assume that this is our outcome B. The first coin came out heads, the second and the third coins both came out tails. Okay, given that this is our outcome, how does this influence our understanding of whether the first coin is the biased one? So that's the event E1. E1, remember, refers to the event that the first coin is biased. We want to understand this probability. Okay. Now, all we have to do is apply the Bayes' law formula. And notice that on the right hand side, we have the conditionality is switched. We are now conditioning on E1. Okay, that's nice because for each of these we already so we know this one. This is a third. That's our prior model. We also know, given that each coin is equally likely to be biased, what is the probability that you will see the outcome be? Okay, what is that? Well, this 1/3 refers to this probability of E1. Remember, B is heads, tails, tails. Okay. So what is the outcome of what is the probability of getting a heads given that E1 given E1, which means that the first coin is biased. So given first coin is biased, what is the probability that that coin will come out heads? Well, we know that it's 2/3. Okay, and given that the first coin is biased, what is the probability that the second coin will come out tails? Well, if the first coin is biased, then the second and the third coins are unbiased. So they will come out tails with probability half each. Okay, so which means that the outcome B is the product of 2/3 times 1/2 times 1/2. Okay, because these three coins are tossed independently. Okay, so now you see that the numerator values, we are able to get all the numerator values. And in similar fashion, you can fill out all the denominator values as well. And if you work it out, it comes out to a half. So if we see the outcome heads, tails, tails, then our posterior understanding of the first coin changes. From 1/3, which was our prior probability that the first coin is biased, noting that that was the only coin that showed up heads, we have been able to update our understanding to say that look, it's more likely that the first coin is the biased one. We cannot say deterministically. We're still not far from being sure about it, but certainly our belief that the first coin is the biased coin has been bumped up, okay, and it's gone to about a half. And if you work out the other two, you'll be able to work it out that these are both a quarter. These are the probabilities that E2 and E3 are the biased ones given this particular outcome. And this makes sense. If both of them showed up as tails, they are not likely to be the biased coin. So this one experiment changed our understanding a little bit, and this still is not, we still don't have complete understanding. We'll have to perform this experiment again. So this 1/2, 1/4, 1/4 will become our new prior model, and we'll have to repeat to further refine our understanding of the worlds. And that's what is shown over here. We started off with 1/3, 1/3, 1/3. We ran an experiment. We updated our probabilities and used these updated probabilities to run the experiment again. And then further we will keep refining, we'll get a better posterior model, which is the individual probabilities of E1, E2, and E3, and that will become our prior model. Run the experiment again. We'll go through this loop a few times. At some point it will stabilize and we'll know that this is the right answer. At that point in time, we're done. Okay. So this is the general framework of applying Bayes' law to understand the world around us. And in this segment, what we've seen is we've shown how to apply Bayes' law in a fairly simple setting, wherein we try to figure out which of the coin might be the unfair coin. Okay, so with that we can conclude our understanding of Bayes' law. Of course, this is just a mere introduction. There is a lot more to this. And I urge you to Google it up and explore some more about it. Okay? With this we come to the end of the first module. So far we've only worked with probabilities and events. And an important notion for, especially in the algorithm design context, is random variables, which we will be studying in more detail in the upcoming second module. Thank you.